such that if I look at the slope of that, I get velocity, and if I look at the slope of that, I get acceleration. I need some function that when I take the slope of the slope, I get something that looks a lot like what I started with, except upside down, with the negative of what I started with. Unfortunately, otherwise it probably wouldn't be in this chapter, there is such a function. So let's talk about how you actually find slopes of slopes. We're going to do it basically from a graphing point of view. There is calculus, if you remember your calculus, for those who have had it. We'll be doing, it's basically first derivative, second derivative.
Great.
All right, so I'm getting an exciting comment right here, and then one of, I think that was one of joy. Maybe I misinterpreted. Again, this is not a calculus-based course, but usually the number of people have had calculus, so I might do it an aside every once in a while, just to get those kinds of expressions. All right, so if I have position versus time here, what can you tell me about that slope?
It's positive.
That's pretty much all you can figure out, but yes. So this is a positive slope. Therefore, my velocity time graph better be positive. Actually, what will my velocity time graph look like? Besides being positive.
It would look like a straight line.
That's a straight line.
No, parallel to the ground.
Horizontal.
Horizontal. Yeah.
Okay. So velocity is positive, and the slope is the same throughout this whole thing, assuming I drew it correctly. Velocity would just be a flat line like that. What would the acceleration graph look like?
There would be an acceleration.
Be zero.
There's a difference between it doesn't exist and zero. Yes, it'd be zero. So my acceleration, actually let's put one right over the top of the other one. I'm gonna give myself a little bit of room. I'm just gonna rewrite those two again. So if I have position versus time, looking like that. My velocity versus time, looking like that. And my acceleration versus time. Looks like that. It's supposed to be on the axis. So for a horizontal line, slope is zero. Here, slope is positive. Here, slope is zero. So obviously, this would not be a proper function to work for Hooke's law. This could not work for Hooke's law because that does not look like the negative of this. We'll do another one that doesn't actually work for Hooke's law, but just to dust off the cobwebs. What can you tell me about that slope?
Negative.
So what would this graph look like?
It would have a horizontal line and negative.
And what would this look like?
It'd just be on zero.
So what would you need to see in the first graph, in my position graph, in order for acceleration not to be zero?
It would need to be exponential graph.
Okay, that would be one example. What, in general, just curved. So I need some changing slope in the first graph in order to have acceleration not zero, at least the entire time. So now let's take a look at just a parabola, or at least part of a parabola. So how do you find the slope of something that's curving? Well, the way that the math people came up with, and for those who could flash back a little bit without bad memories, talking about first derivatives. The way that the math people came up with it is they said, all right, if I want to find the slope at this point right here, I'm actually going to find the slope of the tangent line. So I got a line that skims at that point right there. And so the slope at this point is whatever the slope of that tangent line is. So if that's the case, where is the slope of this curve equal to 0?
At the peak.
Yeah. This is the point where the slope is 0 because the tangent line is horizontal. So if that's my position time graph, velocity time. And so that would be 0 there. What do you know about the slope to the left of 0?
Positive.
Okay. We can get one other thing out of it besides being positive. What can you tell me about the tangent line as we get closer and closer to the peak?
Slow it down.
Yes.
So we start out faster or we're slowing down. And then on this side, what can you tell me about this, the slope?
You're speeding up.
Okay, and? So we're doing this in reverse order of what we did the first time.
So it's,
Negative.
That's the other piece, yeah. It's speeding up and negative. It just means it's going faster in the negative direction. So if I throw a ball into the air, the ball's gonna go up, it's gonna reach the peak, and then it's gonna come back down. So if I say up is positive, the ball starts out at some speed and slows down until it gets to the peak, at which point it changes direction and starts moving faster in the negative direction. And then acceleration times time, what would that look like?
it would look like a diagonal line, or it would. A horizontal line and then a negative line. Negative horizontal line.
Is it 2 lines or 1?
Gonna be 2 lines
What would the first line be?
in the positive.
So, you're talking something like that?
Yeah.
So, if that's the case, because again, acceleration is just the slope of my velocity, where is the slope of this positive? All right, so,
I guess it wouldn't be positive.
okay, not curved. The slope is constant here. So this is gonna be a horizontal line, and it's negative. So if I say up is positive and I throw a ball in the air, basically this line right here is negative 9.8 meters per second squared. That's where that would be on the axis. This is the point at the peak when it changes direction, and that sort of a visual of what it would look like if you mapped it the first time. Yeah, I think you were anticipating that we're gonna get to that, the intermediate step. Now we're gonna get to the function that we can apply to that one.
Alright.
Questions up to here before we get into a function that actually will solve our Hooke's law problem. Okay. Based upon some comments made in the past 2 days, trig is something all of you have seen. What is a,
Sometime in the past few days.
A few days.
based on comments in the past few days that I've got? Some things that you have said.
Oh, okay.
What does a sine curve look like?
Sinusoidal curve.
Okay, there we go. There's the hand gesture I'm looking for.
A sinusoidal curve. Go up and down.
That sine curve. Bring back good times.
Yeah. Good time.
All right, just again, part of the opening bits is just to figure out where you are. Is this completely new to anyone? All right. So this is a sine curve. If this is sine of x and that's x, what is the value of x at this point?
0.
Officially 0 is right here,
That's 360.
Wouldn't that be 2?
not 2. Typically, we're not gonna be
180.
working in degrees right at this point.
Okay, I'm sorry.
So, say it again?
2 pi.
There we go,
Yeah.
finally brought it all together. In terms of the graph, Adam, in terms of the graph, this would not be 0. If we were actually on a circle, when you get to 2 pi, you're also at 0, so it works in that context, but not this context. So this is 2 pi. Let's take a look at what that slope of it would look like. So if this is my position, I had to use x. So we'll use, I'm gonna make that time. So my position graph looks like the sine curve, and my velocity graph, well, let's look at the slopes. Where is the slope of this equal to 0?
Right there.
The peaks.
Okay, I am assuming you also call that a peak.
Yeah.
The maximum and minimum of the graph.
Sorry.
I said the maximum and minimum. of the graph.
Okay, all right. So there, that's, my slope is 0 there, my slope is 0 there, so let's go ahead and get the zeros down. In this first region right here, what can you tell me about the slope?
There's a positive slope.
Okay, and?
It's going
It's
up.
Getting smaller.
Yeah.
Yeah.
So it's a positive slope that's getting smaller. It is actually curved, unlike there where it was a straight line. I'm sort of looking ahead, because I know what the answer is supposed to look like. And what about in this region here between these two zeros?
It's getting.
It's a negative slope.
All right, so we got that part.
It's a negative slope and it's speeding up and then slowing down.
Okay, so as it gets to this point, that's where it's the steepest, that's where you're going the fastest, in the negative direction. And then it slows down again, so, and also I have to connect these two zeros here, so that, and then in this last region,
It's in the positive direction and it's
Going slower.
going faster.
it's one of those two.
It's going up, so it's going slower. Because it's
Slope.
speeding down, going speed is going opposite.
It's,
It's the slope, if you're saying it's slowing down, that means the slope is getting smaller as we go. Is that
Well,
slope getting smaller?
it's going towards 0.
It is going towards 0, I agree with that. But 0 what? It's not going towards 0 meters per second.
No. It's going to the origin.
Right, okay. So he's heading back, so he's
Yeah,
going
heading
away
back
from
to
the
the
origin,
origin.
heading towards the origin, passes it, then stop. Basically turns around and
And
starts
go-
heading back to the origin, but he's heading peak speed at this point right here. So it looks like that. What does that graph look like?
Cosine.
Yep.
That's all.
And then acceleration first time, let's do the slope of the slopes. Where is this slope equal to 0?
At the bottom.
All right, so there. Where else?
at the,
I
the
think.
start
you're-
of the graph and the end of the graph.
Yeah, so here and here. If this thing were going on forever, I just drew one little segment. If it went on forever, then, you know, it would keep going like that, and this would go on like this. It'd be more obvious that we have a peak here and here. So from the first 0 to the second 0 slope, so from here to here, what can you tell me about the slope?
It's in the negative and then it reaches the bottom of the graph where the minimum, and then it goes in the positive direction.
Well,
The slope becomes positive.
okay. And then in this next region from here to here,
It's in the positive.
all right, so based upon Nick's hand gesture, you know what John's saying, it's gonna look like that. What is that graph? Yeah. Tangent has some funky stuff going on.
No, that's gonna be a sign.
Gonna be what?
Hold on. No, that's cosine.
Negative sign.
Sign.
It is negative sign. If you think about our original graph, looked like that, and this is just basically flipped upside down. So acceleration would be negative sign. Which is what we want. If I can, so if something's undergoing, is obeying Hooke's law, the acceleration has to be proportional to the negative of its position, or displacement. And I did a hand wave there, but I'll justify it later. And so if my position is a sine graph, my acceleration is a negative sine graph, well, now I've got negative sign on this side and negative sign on this side. Mathematically, it works. By the way, there are other more complex equations that we can come up with which do the same thing, but ultimately they end up as sine and cosine if you work through it far enough. All right, so notice, if I notice the pattern we have over there, we went sine, cosine, negative sine. So if I've got a negative sine function here, what would the next one be?
Negative cosine.
And then,
Positive sign. So on and so forth.
yep, so it's 0, so this one's gonna look like that, would be the slope of it. So if this was acceleration, this, what is this one called?
Negative cosine.
Right, yes.
Yeah.
If you got position, velocity, acceleration, what would be the slope of acceleration?
Velocity.
The velocity would be the integral.
Displacement.
There were other words.
Speed.
Hold on.
This is some of the best trivia of physics here. All right, so you're at a stoplight, the light's red. Sunlight changes to green. So you're starting out, your acceleration is 0. Light changes to green, you slam your foot down on the gas pedal. What do you feel?
Force.
That is true. I would hope so, because otherwise you're just still sitting there. What does your head do?
Like lean forward.
Momentum.
All right, I think apparently it's involved in to read my mind. Jerk. Your head jerks backwards. This is called the jerk.
Oh, really? Oh, God.
Yeah.
I was thinking it was something fancier than that.
No.
Sure.
There are a couple other words that are used. Jerk is not internationally recognized, but it is recognized in the US. All right, so now let's do the next one. So if we did the slope of this one, we have 0 here, here, and I drew that horribly. There, the slope is positive and then negative. And so we get a sine curve again. But it's the slope of jerk, it's the change in jerk over the change in time, or the first derivative of the jerk. So again, you're at the stoplight, it changes to green, you slam your foot on the gas pedal so your head jerks backwards, but you realize the car in front of you hasn't moved yet. So you slam on the brakes, and so what your head does is this.
It leans. Snaps.
Snaps. This is snap. And what's the next one? All of you know it, because we've all been brainwashed by commercials.
Crackle and pop.
Yep, those are the next two. Snap, crackle, pop. Now,
Okay, so it goes something like position, velocity, acceleration, jerk, snap, crackle, and pop.
yep. You experience snap, crackle, and pop on a regular basis whenever you're driving home.
Whenever I wake up in the morning, my knees start popping.
That too. That's the memory trick. There are two things my mom said that she definitely wanted me to remember. What this was called and what this was called. And this is the popliteal, and the memory trick was knees pop. This is the antecubital, because that's the cubital. That memory trick was not as good, but I did remember it eventually. All right. Snap, crackle, and pop, just from a trivia point of view, there have been 2 referee journal articles, and that's critical in order to get accepted in a larger community, which have used those terms. So it has not been officially accepted beyond basically the US, but the steps have been made. So probably not in my lifetime, but potentially in your lifetime.
So
I've
what
seen
is-
jerking textbooks. I have not seen snap, crackle, and pop yet in textbooks.
What is the official term for that? What is it?
All right, at that point, you have position, and then you have the derivative of position, which can also be written, when you're doing a derivative with respect to time, you can also just write it with a dot there. So this would be the second derivative, third derivative, fourth derivative. The fourth derivative, you could see d to the 4x dt to the 4, or x 2, 3, 4, or if they define it properly, x with a 4 in parentheses there.
So what?
That's the way they deal with it.
What motion is crackle and pop?
I mean, it's just, if you're in stop and go traffic, your acceleration's constantly changing and not at a steady rate. I mean, your head's just basically doing this back and forth as you speed up, slow down. And so that's what it is. I mean, if you were talking something more drastic that would kill you, then there's probably an academic paper out there somewhere which talks about it. All right, all right. So we now have an equation that would actually sort of work for this. We've got to do a couple other things first in order to put all the pieces together.